Hi, my name is Yixuan,
I'm Zhang.
I'm Xinge.
and we are Team 1071 from the University of Florida under Dr. Park. We will be presenting our solution to problem B, narrative influences.
Of our background, researchers have found that people are more likely to recall associations between items when they're presented with a narrative context. This approach can have broader implications, such as influencing public opinions on flu shots and increasing vaccination rates within the population. Our model aims to address the four following problems.
Our model builds upon the DIDT equation from the classical SIR framework, which tell us the rate of disease spread. We adapted this model for problem B within the context of messaging influence. If we treat the positive messaging and negative messaging as two special diseases with no recovery spreading among the population, we can divide the population into three compartments: agree, neutral, and disagree. Similar to the SIR model, the transition rate between these groups are governed by a specific interaction rate, the group being influenced, and the group influenced another. Then we can model how the proportion of population may shift between supporting, opposing, or remaining neutral on a specific issue.
So to simplify our model, we made several assumptions. We assume that opinion changes depend on interactions with individuals from other opinion groups through positive and negative messaging, and note that neutral individuals do not influence others. The likelihood of opinion change increases with the number of such interactions. We also assume that transition rates are asymmetric, making it harder to shift an agree or disagree individual back to neutral than to move a neutral individual to agree or disagree. We assume that individuals change opinions sequentially, moving step by step. For example, a person in the agree state must transition to neutral before shifting to disagree. We further simplify interactions by assuming individuals interact randomly and uniformly, with no individual differences. The total population remains constant over time. Individuals only change their opinion states. Finally, all opinion changes are driven solely by interpersonal interactions, excluding any other external influences such as social media.
In our model, AT, NT, and DT represent the proportion of population in each group. Since we model information transmission as infectious disease, all of our parameters will be related to messaging transmission rate between populations. Interaction rates between these groups are denoted as betas. For example, beta AN is the rate at which agree individuals become neutral due to interactions with disagree individuals. And beta ND is the rate at which neutral individuals become disagree due to interactions with disagree individuals. And of course, we have beta DN and beta NA. Here's a breakdown of our parameters on the right, and we can see by these equations on the left that dAdt equals to beta Na times N times A minus beta An times A times D, represents the change in the agreed population. Similarly, we have the rate of change in the disagreed population and neutral population. Note that the equations are analytically unsolvable and the system has only numerical solutions.
So to find the equilibrium points, we first set the derivatives to 0, and we express D in terms of A, and then we express A in terms of beta, and when dAdt equals dddt equals 0, dndt is automatically 0 by the equation A plus n plus D equals 1. This gives us three types of equilibrium points. The first one is the trivial solution, A equals D equals 0, and the second is the asymptotic solutions when A equals 1, D equals 0, or A equals 0 and D equals 1. The last type is the parametric solution as derived in terms of A and D on the right-hand side. Next, we look at the results of our sensitivity analysis. So begin with scenarios where agree group starts with an initial predominance over disagree individuals. We can see that a high beta NA results in a rapid increase in the agreed population. Conversely, most individuals become disagree with higher beta ND, even though there's an initial advantage of the agree group. When beta values are symmetric, the transition rates are more gradual, and the agree group dominates in the end due to its initial predominance. In the loss graph, lower transition rates slow down the change of opinions, and it shows greater stability and resistance to change. Next, we look at the scenarios where the disagree group starts with an initial predominance. Similarly, the agree population dominates with higher beta NA. Disagree population dominates under higher beta ND. When parameters are balanced, the group with the initial advantage will dominate in the end. Lower transition rates slow down opinion changes. And our model highlights the importance of strategic communication. The interplay among different beta values determines which opinions become dominant. We can use narrative messaging to change the beta values. To benefit public health and economy, increasing the vaccination rate is important. This can be achieved by enhancing beta NA and beta DN to promote positive messaging and counter negative narratives, and reducing beta ND to limit the impact of negative messaging is also really important.
Next, we conclude a case study related to COVID-19 vaccine attitude. We obtained data regarding attitude toward COVID vaccine from the research COVID-19 and vaccine hesitancy and applied Euler's method to predict the proportion of population for each group over time. The raw data are respondents' answer to when there is a vaccine for the coronavirus allocated. Under a 7-point scale, 1 representing strongly disagree and 7 representing strongly agree. The survey was once per month from March 2020 to September 2020. We classified 1 to 3 as the disagree group, 4 as the neutral group, and 5 to 7 as the agree group. Then we calculate the observed proportion of population for each group. We applied the least square method to find the interaction parameter of the model. Leveraging Euler's method and SciPy and Pandas library from Python, we predicted the proportion values over 6 months and compare them with the observed values. For the graph on the right, notice that the predicted value well fitted the observed value. In this scenario, beta NA and beta ND are greater than beta DN and beta NA, respectively, which shows the negative messaging is more efficient. Moreover, we have made predictions for proportion of the population of the 3 groups for 100 months. We can tell the negative messaging take dominance over time and the whole population is finally turned into disagreement. An equilibrium analysis was also conducted for this case study. The vector field graph demonstrates how the proportion of population for the agree and disagree group changes over time. Points where arrow converge indicate the potential equilibrium state. So, next slide. Corresponding to what we have mentioned previously, there are 4 equilibrium points. Points 1, 0, and 0, 1 represent asymptotic equilibrium. 0, 0 show a trivial equilibrium. Additionally, we can see a stable equilibrium at points around 0.8, 0.1. We can demonstrate the border health impact using the SIRV model. We create a SIRV model, and on the right are the definition of the variables and parameter. If there are more people who agree, the rate of vaccination increases. Therefore, V is positively correlated to AT. That's how we simulate the health impact of our model. According to the research adaptive SIR model with vaccination, we selected suitable values for the initial condition and parameters. We control all these parameters and manipulate the vaccination rate. Referring to the graph on the right, when vaccination rate increases, the infected population decreases.
While our model provides valuable insights, it has several limitations and room for future improvements. Firstly, real-world social networks and interactions are structured within communities for online networks, and external factors such as media, advertising, policy interventions, and shifting public sentiment can impact opinion dynamics. Our model can be improved by taking these elements into consideration. Moreover, the assumption that individuals cannot directly switch between agree and disagree groups without passing through neutral may not always hold in real-world situations. The model does not consider individual differences in susceptibility to influence or persuasive ability. And interactions are assumed to have immediate effects, disregarding delays or the accumulation of persuasive efforts over time. These limitations highlight areas where the model could be refined for greater realism. These are the references we use for our study. Thank you very much for listening.